Hey, howdy everyone. Today we're going to get into linear regression. We have previously been talking about bivariate statistics. We have covered the concepts of correlations. We did a discussion about general features we would look for in looking at scatter plots. Got to use words like heterogeneity and talk about bivariate outliers. And of course talked about bootstrap, which was fun. Now we get into the concept of linear regression, and we'll shortly get into concepts around spatial statistics. When I introduce linear regression, I like to do so in the context of the most simple form of machine learning possible. If you think about it, machine learning is teaching a machine to learn the relationships between features and a response based on or driven by data. We're trying to formulate a relationship between a series of predictors or features, which are represented by x1 through xm, where m is the number of variables or features available to you, and you have a response. For this case, we're just considering a single possible response, y. And so we also would imagine that in this model there will be some degree of error. We won't have a perfect match to our data. And so, but of course we don't know f. F is not provided to us, so we have a problem of the following. We can simplify it down to an estimate of y indicated by y hat is equal to a function, which is a function hat because we're estimating the function as part of our statistical learning or machine learning approach, based on a set of features or available predictors that we have to work with. And so we just indicate that that function is itself an estimate. And so this is the fundamental prediction problem. Is how do we make a prediction of y? We have to estimate f in order to take the available knowns or features in order to do that. Now, we always take advantage of the opportunity for inference, because when we're building these types of models, we're also learning about the general relationships between all of the features with regard to each other, and also the features with regard to the response. And so in doing this, we're actually solving a bit of an inference problem of understanding these relationships that can help us with so many things, such as what variables to focus on, how do we do dimensional reduction, how does uncertainty propagate through the model, and so forth. So we're going to learn, we can learn the relationships between the features and predictors. Now, the simplest form, I think, of statistical learning or machine learning is linear regression. And so we'll just cover it really quickly right now for the case of a single feature and a single response. Now, later in this course, we will return to statistical learning and we'll cover much more complicated methods. We'll get into dimensional reduction, we'll talk about decision trees, random forest, and so forth. There'll be a lot more that we do on this topic. So, let's set up the problem. How do we build a prediction model for a porosity given a measure of, and why would we want to do that? And so one good reason would be perhaps we find that the porosity measures are not available everywhere. That instead you have some other measure, such as rock density, that is available widely, frequently, and we can relate it to porosity. Well, this could save cost and time if we're able to take that data directly as a proxy and use it to, well, basically to model our way to get to porosity. So once again, we promised we'd deal with one feature and one response. So we're going to build a linear prediction model of the following form. The dependent variable, the response, is equal to an intercept, a b naught, plus a slope multiplied by the feature. And so here's the data set that we're going to work with in order to try to demonstrate this approach. We have a number of data, probably on the order of about 100 or so, and we have density and porosity, and you can see a pretty good relationship between the two. So we're going to build ourselves a prediction model of porosity given density. It will have the following form. I specify just using short por for porosity, B0 plus B1, the slope multiplied by a density measure. So our objective is to find or to fit the B1 and B0 coefficients of our linear function in a way such that we minimize the delta y's, i's, over all of the data locations. The delta yi's, the I is an index for the data going from 1 to number of data. And so if I gave ourselves a very simple example right here, we have our linear model, which is fit by the intercept and the slope parameter. We could then, with our model, for any given x value, we could then predict an associated model estimated y value. And so for ourselves, we have the data which are located here, 1, 2, 3, 4, and 5. We could go ahead for each one of those data values and calculate the model value that we would predict with, our estimate from the model. And the dashed line is showing the difference, and each one of those differences would be a delta yi, delta y1 through 5. And so we want to limit or to minimize these delta yi's over all the data. And a very nice way to do that would be some type of a minimization of the squared error term. And so our squared error term would just be the summation of these delta yi's squared. And of course you could replace or expand this to say delta yi is equal to the data value minus the estimate, and the estimate is equal to this model which we have here. And so this is effectively what we're trying to minimize. Now there's a whole derivation that we skipped here, but if we conduct that minimization, minimize that squared error at the data locations, we would get this equation for the slope. And you can notice it's just a big long product sum of each of the data values centered by their mean for the first data set, x, the features, and for y, the response. And that is all going to be normalized by the sum of the squares of the data values in the feature minus the mean. Once you've calculated B1, it's quite trivial to substitute into this equation any one of the example data points or the mean in order to calculate the intercept, the B0. And that would be your linear model to relate density to porosity. Now, of course, there will be some assumptions with that model. And here's a list of assumptions that we need to make in order to calculate and to use that model. First of all, we have to assume that the predictor variables themselves are error-free. They're not random variables, they're constants. They are known without any significant degree of error associated with them. We also have to, and this is pretty obvious, we're assuming that the response is a linear combination of the features. Like in the case of the model we're building right now, porosity is just a linear relationship with the density. We can fit it with just an intercept and a slope, and there we go. We're not able to fit curvilinear types of features that are nonlinear with regard to that relationship. Constant variance, that is homoscedasticity. The error in the response is constant over the range of predictor values. So it should not be changing based on the predictors. That variance should stay the same. Independence of the error. So any error in the response is uncorrelated with each other. There's not systematic or correlated error within the response, and there's no multicollinearity, which means that each of the features provides unique information. None of them are combinations of the other features. Now you notice in this description I've kind of switched back and forth between feature or predictor. They're synonymous with each other. Okay, so given all that, we can go ahead and build this model and use it. Now, I've worked out this in Excel with a spreadsheet so that we've done the whole thing by hand. You notice that we have a set of data samples that are available to us, and we're going to need centered values. We're going to need product sums of centered values to put in the numerator, denominator. We're going to need the square of the product sum of the feature for the case of one feature, of the feature centered itself, and a variety of other measures are required in order to calculate the B1 and the B0. Once we've done that, we can then go ahead and we have our model. Remember, two parameters, B1, slope, B0, intercept, and we have a complete model of the relationship, a linear model of the relationship between density and porosity. Now, the original data is shown again. I've shown the original data as a black line indicating their values in space over depths from 0 to below a datum to about 27 meters. And you can see the black line is the actual porosity values, the true values that we were training with. Now, if you look at the red line here, the red line, in fact, is our relationship, our model, our linear model of porosity given density. So with this model, we can get porosity for any given density. And you look at the model and you can judge that it's pretty good. It has a pretty good fit to the data. You see quite a bit of scatter. There is error, and that makes sense. It wasn't a straight line in the data, so we expect that there is going to be some error. The red is in fact the predictions of porosity from our model, and you can see that there is at times some divergence. Other times we behave quite well. So we have a model that does reasonably well. Now, I am a fan of Excel for doing linear regression from the standpoint of understanding what's going on. And plus, I do appreciate the fact that Microsoft Excel does provide you with quite a few useful outputs when you do linear regression. And so in this demonstration right now, I will show linear regression in Excel because it's very easy to work out by hand. Plus, you get all of the outputs really nicely. And so I find that very useful. So I have an Excel spreadsheet that's available on GitHub. It's called Linear Regression Demo version 2. Much better than version 1. Kidding around, but use version 2. That's the one that I'm showing here right now. Let me go ahead and I'll put it on the screen. I'll zoom in a bit. You may not be able to read everything at this point. You won't, of course. But just to show you what's going on from a macro view, I have a bit of a methodology here in order to calculate a bi-Gaussian or two-variable Gaussian relationship. You're going to have the mean, the standard deviation, the mean, the standard deviation of two separate variables, and then you're going to have the correlation coefficient, which perfectly describes the relationship between two variables if they are bivariate Gaussian. Then, so this first lines here are all about just building that set of data. And so when you set those parameters, you'll end up with something like this. This is the resulting density, porosity, and that comes from those parameters. And it looks pretty good, but it is clearly a bivariate Gaussian. Then you'll notice that there's well logs that come about, and those well logs are calculated going from a 0 datum down to about 27 meters, 26.5 meters, sampled, I think, at quarter-meter intervals or something like that. All of these lines of code over here, or Excel columns, are because I'm imparting correlation. So it's not just random. There's spatial correlation plus the correlation between the two variables. So I think that suffices it to describe what I was doing there. Now, these columns right here are the by hand calculations that are required to calculate B1 and then B0 and to fit the model. So, and I also calculate at this point here, the actual fit value, the estimated value for porosity, and then the residual, the error. Okay, so all of that is very helpful for everything else we're going to do. Now let's get back to linear regression. Just to get started, I did a correlation coefficient calculation, and I do compare that to R squared to prove the fact that correlation coefficient squared is equal to R squared. When you have two variables and you do linear regression, that's nice to know. But this is the calculation of B1 and B0. This is the model that's fit. These are the residuals, the error over the porosity values, which is very useful to identify if there's a systematic bias within your model. You'd be concerned if over some ranges of porosity values you tend to be above the line. That suggests that you're overestimating. Your estimate is greater than your true, or you're below the line, your estimate is less than your true. If you saw something was systematically you overestimating, then it would suggest that there's a general bias within your model, a conditional bias, and we would be concerned about that. So we want to check the residuals, make sure they're centered on 0, and so forth. The linear regression calculation within Excel has the linest command. It's pretty straightforward to use. The only complexity is it's an array command. So in order to use it, what you do is you select a set of cells that's large enough to have all of this data. Note, if you have more than one variable, you're going to have to expand it over in order to fit all the additional information. You're going to select that set of cells, type in the command, and you're going to hold down Control, Shift, and hit Enter, I believe, in order to enter an array command. Then you'll get this output. If you go to the Excel linest docs, it'll explain what each one of these values are. What I've done here is I've actually taken each one of them and copied them into these cells here, explained them, provided a little bit of additional information, and so then we're able to use each one of those outputs. And this is part of the reason I do like Excel for linear regression, is you get enough information here to do quite a bit. The first thing is you can do a significance test of the coefficients. The significant test of the coefficients, say BI, 0, 1 if you have one variable, 2 if you have another variable, 3, and so forth, is simply going to be a test of whether or not these parameters, model parameters, whether or not they are different than 0. If you fail to reject that null hypothesis, you can say that that parameter is perhaps not statistically significant, that it effectively could be just a random effect due to limited sampling in the data set and may be actually equal to 0. And so we can run that test. Actually, in order to calculate the t-statistic, all we need is the coefficient, say the slope, or the B1, divided by the standard error of the slope, and I'll show you in the notes how we calculate that. You can, of course, using the student t-distribution, you can go ahead and calculate the probability, and you can compare that against your alpha level and decide, or you can just use the resulting t-statistic compared to a t-critical, and you can decide if you are to reject and determine that your parameters are significant, or you fail to reject and determine that perhaps it is not meaningful or useful to you. And so you can do that based on using the probability or the t-statistic and the t-critical value. You can do that both for B1 slope, B0 intercept, and that's shown here. In addition to that, there is a test of significance that's based on all of the parameters at once using the F statistic. And so the F statistic is provided for you right here. And you can use that to test using that statistic directly and looking up from the F distribution, the one-tail, right-tail test using your alpha level. You can calculate the F critical value, and that's shown right there. And so that really is based on the idea of, does your model explain enough variability that it should actually be a significant model. So it's testing the whole model at once. So that's pretty useful. And then these two final parts right here, you get the confidence intervals in all of the coefficients. And so the confidence interval for the slope, you can calculate that directly by using the slope itself plus or minus the estimate of the slope plus or minus the standard error of the slope. And you're going to multiply that by the t-critical value at the specific confidence level that you want to work at. The prediction interval is shown right here. What's really cool about that, it's a bivariate prediction interval. So it is given you know the density, what is the uncertainty distribution in the very next sample for porosity. And that's very powerful. That's a really powerful thing. And we'll show in the notes how to do that. So I like Excel because you can do all this by hand. All of these outputs are very useful to getting all of the prediction, confidence intervals, hypothesis testing, and so forth. And for completeness, I explain each one of those outputs from the Excel linest command right here. I'll also give you a little bit of, just a little bit more discussion about this. I show the actual results once again here and comment on R squared. R squared is provided directly to you it is the proportion of variance that's explained. We have about 63% of the variance explained by our model. Now, the way to think about R squared is it is the sum of squares of the explained by the regression model divided by the sum of the squares, or the total variation, which is the sum of squares of the regression model explained by the regression model, plus the sum of squares of the residual, the error, the part that you didn't explain. And so if you look at the equations, they make sense because the sum of square of the regression model is simply going to be the sum of the square of all of the estimates centered. And so that's the amount of variation within the model. And then you have the sum of squares of the residual. These are the error terms, the difference between the data and your estimates. That's the part you missed. And so it's really cool. That R square value is very powerful. And note, once again, in the bivariate case where you just have one feature predictor and one response, and you're using linear regression, you'll find the R squared is just equal to the square of the correlation coefficient. So without doing a linear regression model, you can predict the R squared, or variation described by a linear regression model, just by using Pearson's correlation coefficient squared. Okay, so that's R squared. We should also comment on the test for significance of the parameters or the model. The F statistic, or the F test for significance of the entire model, is very useful. It is a ratio of the mean squares of the model divided by the mean squares of the error. And the equations are specified here. They incorporate a different number of degrees of freedom. Specifically, if we're talking about mean squares of the model, we would consider K being the number of parameters of the model minus 1 as the degrees of freedom. We're working with the mean squares of error. Now we're dealing with all of the possible estimates in their error. So we get the number of samples minus the number of parameters for that degrees of freedom. And we get a number like this, and we'll compare it to an F critical based on the alpha level and the degrees of freedom as specified here. K minus 1, 2 parameters minus 1, that's 1. N minus K, that would be number of data minus 2, because we have 2 parameters in the model. And of course, we got the rejection criteria shown here, and so forth. The R, which is really cool, R stats, or regular R, does this automatically. Excel will provide you the F statistic, and you need to calculate the critical value to then do your own comparison. And we've done that. Confidence intervals of all the coefficients, that of course is also available to you. And I showed how to do that in Excel. That is, you can find that in R. That's done very automatically for you. It's very nice and clean. And the prediction intervals and their associated equations are shown right here. Always remember, a prediction interval is with regard to what will be the next value of on the response variable given knowledge about the predictor variable. And so it makes it a conditional uncertainty model. Very powerful. So this is one thing I should also comment is R has a function that's built into it that's able to calculate the confidence intervals for any value. Now I keep mentioning the fact that R, we could do this in R, and so what I've done is I put together this same example in R. It has an R file, an R markdown file, and a knit HTML doc from the R markdown file. So it's pretty clean, and I do a lot of comments. These files are all available, linear regression _demo_ version 2 R markdown and HTML are all available on GitHub if you want to check them out. And so the workflow in the HTML, which is the knit R markdown, is shown right here, and you can step through it. It has all the steps of linear regression, including all of that stuff around hypothesis testing of the coefficients, confidence intervals, prediction intervals, and so forth. I can't help myself. I want to show it to you. So here is the HTML file that was produced. Let me zoom in just a little bit on it, just so we can see. I think that should be pretty good. And so it steps through all of the steps, including loading the data, visualizing the data, doing a little bit of data checking, seeing what it looks like. Here's the relationship between well porosity and well density. We can go ahead and look at the univariate statistics, see what's happening as far as the histograms, CDFs of density, histogram, CDF of porosity. Of course, even when we're doing bivariate analysis, we want to go back to univariate analysis, see what's going on with our data, look for outliers, the same types of issues, right? We want to go ahead and we can use the linear regression command. You can notice, once again, super simple to use in R. The porosity linear regression model is just por tilde den. Those are the two variables from the MyData data frame. We're just telling it to give us a linear regression model of porosity given the single feature density. We have the opportunity to do some QC of our model. We can go ahead and get a summary of the model, and this object right here is now the summary. We just tell it what the model was, and we can look at that summary. It includes a lot of things for us. If we look at coefficients, it's going to tell us the intercept and the slope. In other words, the B1 coefficient with regard to density gives us their estimates, their standard errors, their t-values, and their probabilities. Once again, these are symmetric probabilities from the student t-distribution. If we have a value less than alpha, we reject the null hypothesis that the parameters are equal to 0. If we have a value that's greater than alpha, we're going to go ahead and fail to reject. We also can look at that summary and immediately get the result from the F statistic, the F test, where once again we're looking at the entire model at the same time, specifically with regard to how much variability is described by the model. Is it possible the model is in fact not describing anything to us? And we can test that using the F test. We can do some QC where we print up the residual distribution. So we're looking at the error at every single one of our data values. How much are we over and underestimating? And this is very useful. We want to see if we were centered at 0, so we could calculate the summary statistics and make sure we're centered at 0. Look at overall quartiles. We could look at whether or not we have like extreme outliers. Those would be locations we look specifically to see what's going on with our model. Why is our model getting that wrong? And then of course we have the summary command where we can just run that on the entire linear regression model, and we can just look all at once at basically most of what we just talked about just now. So it's very, very efficient in order to do that. We also have access to built-in methods to do confidence intervals. And so all we have to do is say conf int the regression model, the level we want to work at, and boom, we get the confidence intervals for the parameters in the model. The 95% at the 95% confidence level, we get the P 2.5%, the P 97.5% for each one of those. Very, very powerful. And then finally, well, it's very easy also to do predictions. You can supply a brand new set of variables in, and you can get the predictions and specifically built into it prediction intervals. The model prediction, the 2.5 percentile, and the 97.5 percentile, the lower and the upper, are provided to you, so you have the prediction intervals also all at once. So that's all I'm going to cover right now as far as R and doing linear regression. There's some other, of course, checking methods right here. I've included those and also provided some description of what each one of those are and how you use them in order to detect bias, to see whether or not your model is meeting specific assumptions of residual distributions and so forth. All of that is very useful. So that was my discussion on regression analysis. In a way, I'm apologetic because I know it's a very practical approach to it. It's more about how to do it. I did very much glance over or not go into depth about specific assumptions, the mathematical derivations and so forth. There is, of course, we want to be careful, go back and review and look at that list of assumptions. We want to be careful with using this type of methodology. I did not talk about extrapolation with any type of modeling. Of course, we want to be careful about if we use the model outside of the range of data features that were provided to us and so forth. But I still hope that this was helpful as a very simple, straightforward initial introduction to regression analysis, which really is the most simple form of machine learning. And we're headed there. Next, we'll get more into some spatial statistics type methods, and we'll get eventually into machine learning proper. All right, I hope that was helpful. Thank you.